Okay, today our big theme today is to do a new type of proof. But before we do a new type of proof, we're going to go over some of the basics of manipulation of unions and intersections and things. Now, past history has told me a lot of your computers do not translate all of the symbols well. So for this chapter, I'm actually saving everything as PDFs rather than as Word documents, because some of your computers won't actually interpret the symbols, particularly unions and intersections, and I don't know why. They have tremendous difficulty with those. So I want to go over some very basic terminology and definitions. I want to make sure I have them all in front of me. What it means. So, for example, if I said that X is an element of A union B, if I said X is an element of A intersect B. Now, assume that A and B are sets. What do each of these statements mean to us? Because this is the foundation of how we're going to write our proofs, is the basic premises that we're going to make right here. For X to be in the union. So what I always like to do in these kind of situations, I love using Venn diagrams because the visual sometimes makes it so much easier. Now, what is the union? Anybody? In this picture, what is the union? Because I want to make sure our vocab is flawless here. So what part of my picture? Anybody?
I believe it's the entire Venn diagram.
Careful, because if I'm here, I'm outside of A.
Or inside the Venn diagram.
I think it's inside of A and B, you know, that section where they
That's kind of what I meant to say.
So this.
No, just the intersection of A and B inside of.
Yeah, that's what I'm referring to. That's what you stated.
Okay, no, the entire Venn diagram, this would be the entire universe.
No, I mean inside the circles, inside the circles.
Yeah, inside the circles. There we go. That's why I said we got to make sure we're all on the same page. This would be every outcome. This would be the outcomes that are in A or B or both. That's probably a safer way to say it, or both. Now, a lot of folks get confused. Do I count this or do I leave that out? Well, this says I'm in A or I'm in B or I'm in both. That's really what that means. So X in A union B means what? X is in A or X is in B. It can be in both. That's nothing wrong with that, but it doesn't mean it's excluded from this. Okay. Now, the second one, X is in the intersection. Well, which part is the intersection? Intersection we know is the overlap. So the second one, I am only in this portion here. Now, this is the one where a lot of folks get them confused for obvious reasons. This says X is in A and X is in B, and that and is critical. And and or mathematically are not even remotely similar concepts, right? I can be here in this portion here and I'm in the union. I can be here and I'm in the union, but only in here am I in the intersection. If I'm out here or I'm out here, I'm not in the intersection because I have to be in both simultaneously. So we want to make sure that we know exactly that's what this means here. Now, continuing. Okay. What if I said X is in a complement? Now that one's a little bit trickier from a Venn diagram standpoint. What does it mean to be in a complement? First of all. Well, what part of the picture is a complement? Well, that would be everything in my rectangle that is outside of A. So to be in a complement simply implies that X is not an element of A, and that's the correct way of saying it. Being in A complement means I'm not in A. Now, there's another one that gets us in trouble all the time, and this one I'm going to define for the first time today. This one's a very powerful one that we like to use, and it's what's called set difference. And that can be a little bit confusing. A set is not a numerical quantity. So how do you take a difference of sets? Well, it's how we define it. So if I said Let's say set A is A, B, C, D, E, and let's say set B is A, B. I want the set that is everything in A, but the stuff in B removed. Now, a lot of times people will use this. The backslash symbol means remove or delete. But what we're really going to say is just simply A minus B. We're going to define set subtraction as the removal of items from a set. Now, here's the critical thing. All of B has to be in A for this statement here to have any meaning, or does it? Does everything? What it basically means is everything that's in B that is also in A, I'm going to remove. So A minus B in this case would be C, D, and E. So the question is, what if I do this? I'm going to add that element to the set. Is this still the same thing? I want to remove all of B that is in A, which means I'm removing the A and the B. So from a Venn diagram standpoint, to make this make sense to us, okay, here's my A, here's my B. I'm going to do the second one here. So in this picture right here, I've represented these guys and I want A minus B. So if I'm removing B from A, it's only leaving me this portion here. Okay, so what does this mean in terms of unions and intersections? Well, what is B complement right now? What is the complement of B? The complement of B would be everything outside of B, including a great deal of A. The blue stuff right here is B complement. If I said, let's take B complement and all of B complement that is also in A at the same time, then this would be the same as saying A intersect B complement. So from my picture, I want to make that absolutely clear. So it turns out one of our most important formulas that we're going to learn today is this one right here. Let me go ahead and state it. And this is generally referred to as the set difference law. We like using the word law. And that's that A minus B is equal to A intersect B complement. And that is always true. If I take everything outside of B, what part of that is in A is the same as saying, let me take everything in B and remove it from A. So if I take everything in B that's currently in B and remove it from A, that's the same as taking everything outside of B and intersecting it with A. So this is a very, very important one. This is useful because I can manipulate this. We have De Morgan's laws, we have the distributive laws, we have commutative laws, we have all the laws of unions and intersections that we've seen before. So if I have something that looks like this isn't particularly useful if I want to combine it with other rules, so we replace it with this. So from a De Morgan's standpoint, if I had something like this, for example, if I had A minus B and I wanted the complement, well, what would that be? Well, that would be A intersect B complement. Now I can use De Morgan's law. De Morgan's law says the complement of the intersection is the union of the complements. So this would be A complement union the complement of B complement. Now, some people will do two steps to do that. They'll say B complement, and then simplify that. I'm not a big fan. I'm just going to write B. Okay, so this would be equal to this. Okay, so in my picture, A minus B, I'm running out of space. A minus B was this part in here. Okay, if I said, what's the complement of A minus B? It'd be everything else in my picture, including the A, the B, and the F. Well, that's the complement of that. I'll say, oh, okay, so now when I look at my picture, that's A complement union B. I get the A and the B back again. It's kind of fun. I like Venn diagrams. Now, Venn diagrams in this context aren't as useful if I throw in a third set, but that's for another day. Okay, now we've defined that guy there, and we're going to go through all of the laws at some point, probably today even. Now we want to talk about combining things in general. And so we've done this before. We've done it with summations and we've done it with products, but what about unions and intersections? What if I said something like this? I want the union from I equal 1 to n of AI, where the AI are sets. So I have set A1, set A2, set A3, all the way up to set AN. This is notation now. I'm going to introduce. This says the union from I equal 1 to 10 of AI. That simply means A1 union, A2 union, right? Union. I'm going to do the union of n sets. Okay, so we've done this with a summation from I equal 1 to n, add them up from I equal 1 to n, multiply them as a product. Can I also do that with something like this? Sure. Let's define AI as being, how about this? AI will be the following. It'll be AI plus 1, AI plus 2, and AI plus 3. Okay, let's just say that's what it is. So that would mean set A1 is A1, A2, A3, and A4. Set A2 is A2, A3, A4, and A5. Now I can keep doing this for a while. So let's say in this context, with this definition of AI, let's do let's say I equal 1, let's keep it simple, I equal 1 to 4. So I want A1, union A2, union A3, union A4. So let me write A3, A1, A2, excuse me, A3, A4, A5, A6. Okay, again, it's going to match. And then A4, A5, A6, A7. So I want the union of all 4 of these sets. Well, for example, A4 happens in each set. So does that mean I write it 4 times? Anybody? How many times do I write A4? Anybody got a number?
Just once.
Just once. Yeah. If I said, I'll keep it really simple. I'm going to have a party and I'm going to invite everybody in Calc 3 and everybody in discrete math. Well, some of you are in both classes. So does that mean you count as 2 people when you come to my party? No, you count as 1. You just happen to be in the intersection. That's all that means. So you still count everything only 1 time, but what is going to be counted in this case will be A1, A2, A3, A4, A5, A6, and A7. So that would be the answer to the question. Okay, now I'm going to define a new symbol, and I think you can all figure out what this one means pretty easily. I want the intersection from I equal 1 to 4 of AI. Now, what that would mean is the mutual intersection of the 4 sets. So using the previous notation, this would mean, so I should make my A's look less like my intersection symbol. Now, one thing we do know about unions and intersections are commutative and they are associative. So if I said, I want the union of 2 sets, it doesn't matter what order I write them. I want the intersection of 2 sets, it doesn't matter what order I write them. I want the union of 3 sets. I can write them in any order. I want the intersection of 3 sets. As long as it's all intersection. If I throw a union in there, no, that's totally different. I need parentheses at that point. But if I said I want the union of a bunch of things, that would be like in algebra saying I want the sum of a bunch of numbers or I want the product of a bunch of numbers. The order and how you group does not change the answer. So the order I write these or how I group them. So technically you can say, well, I'm going to do the first one first. And when I get that result, then I'm going to do it with the next one. And then when I get that result, I'm going to do it with the next one. That's okay. Or you could have said, I'm going to take this result and then I'm going to go like this. And then I'm going to go like this. It doesn't change the answer. And in this case here, what would be the answer?
Just
A4.
A4.
The set that has only A4. Beautiful. Beautiful. The set that has only A4. So now I'm going to do one more. What if I had the intersection from I equal 1 to 10 of AI? Oh. I went just beyond our reach there. What do you think? Is there any element that is in all 10 sets?
No.
No. So usually the simplest way to write it is, what does that mean? Anybody?
Empty set.
Empty
It's
set.
empty set. Yeah. Empty set is the set with nothing in it, but it's still technically a set. And that's where we get in trouble. It is still a set. So I didn't lose the fact that my answer is a set. A lot of people go, I like using this symbol, which I've never used in my entire life for 1,000 different reasons. One, it's a symbol, it's a thing, it's a physical object, and you can't actually have anything. Secondly is about 3/4 of you make all of your zeros look like that. And if we were in Calc 3, all of you make your angle phi look like that. It's the worst symbol ever in the history of worst symbols because it's the symbol people use. I find this is the funny thing is when I see the symbol, it means zero, it means infinity, it means undefined, it means DNE, it means empty set, it means whatever the heck you want it to mean at that time, which of course, every one of those is completely incorrect. No, never use that symbol for empty set, use that symbol because we have cardinality of sets. Sets and elements are different things. Ooh. You're writing a symbol that looks like an element when you mean a set that has nothing in it. And the set that has nothing in it shouldn't look like a thing that has something in it. It's a terrible symbol. Always use empty set. I was fortunate early on in my math career that I had instructors who said, you're right, use that symbol. I'm going to mark it wrong. I'm not even going to look at it because they found people use the symbol for every single kind of answer you could possibly give. When I did factoring in remedial algebra, and you had a polynomial that you couldn't factor, so the answer was prime, of course I got that symbol, which has absolutely nothing to do with it. I get that symbol with no solution. I get that symbol with dependent system and inconsistent system and linear algebra. It's like, that doesn't make sense. It's not in the same universe of answers. Yeah, so empty set, and that is a totally reasonable answer. Okay, so if I said I wanted a union, you're never going to see an empty set answer. But if I said I wanted a large intersection, empty set is actually a very common answer because there would have to be something that is mutually in all sets simultaneously to get something there. Okay. Now, a little bit later, we're going to talk about the cardinality of sets. That's how many things physically are in a set. So if I said, what's the cardinality of an empty set? You'd say it's 0. So there are times when you will apply a numerical value to a set, but that numerical value will always be a whole number. A whole number, remember, it's neither z plus nor z minus, it's z plus with 0. Okay, because I can have nothing, but I can't have negative number of things. I can't have a decimal number of things. I can't have a fractional number of things. So this is fairly simple notation. Now, the other one I want to review, because it's going to come up, is the Cartesian product, which we did on day 1 of class. So I'll keep it simple. If set A is AB, set B is, let's say, alpha, beta, and set C is 1, 2. I'm going to keep these small. First, A cross B, that's the Cartesian product of A and B. Now remember, a Cartesian product produces things that look like, well, it looks like points on the XY plane in a sense, because that's exactly what's happening. So this would be the set of ordered pairs, and the order does matter because it matters which one was first. So elements of A are in the domain, elements of B are in the codomain. So this would be A alpha, A beta, B alpha, B beta. Now, could I do these in a different order? Could I have said A alpha, A beta, B? Yes, because there's no order implied in a set. So what if we go now to linear algebra calc 3, if I said, what is R2 in simple English, you'd all say that's the XY plane. That's the real XY plane. And you're absolutely correct. But technically, what is R2? R2 technically is the Cartesian product of the real numbers with the real numbers, because I'm generating now every conceivable ordered pair of a real number with another real number. It's kind of cool. Oh, I didn't think of it that way. Yeah, that's all 2 dimensions is. Now, what if I want to do another Cartesian product? Just to be thoroughly evil, I want to do A cross B cross C. Now, this is something you probably haven't seen before. This is not hard. So what is this going to look like? Well, it's going to still be this, and it's still going to be ordered pairs, but not the usual ordered pair. My domain now comes from this set of ordered pairs. These 4 ordered pairs are my elements of the domain. So the first entry here would be A alpha, comma, 1. Oh my gosh. An ordered pair within that. A alpha, sorry, can't read my own writing there, comma, 2. Then what? Then A beta, comma, 1, A beta, comma, 2, and so on. I'm going to have exactly 8 elements. The last one being B beta, comma, 2. That would be the last of the 8. Now, again, this is unusual. We've never seen it look like this. But the parentheses here say, no, I'm going to treat this as the first thing. Whatever this is going to be the first element of this. What if I wanted, let me ask you, what if I want an element that looks like A, comma, B, comma, what if I actually want it to look like an ordered triple? I don't like the parentheses within the problem. Okay, what if that's what I wanted? Does anybody want to try? How would I? And it's kind of the same thing. I want to generate R3 as real numbers, real numbers, real numbers. How do I do that without inner parentheses? No parentheses here. So if I said A cross B cross C, then the answer would look like things like this. Oh, so that's how we get R3. It's R cross R cross R, but I'm not grouping them, because by grouping them, I'm putting a priority on them. Now, do we ever do things this crazy? Do we ever look like that? Actually, yes, this is all of Calc 3. All of Calc 3 looks like this. How does all of Calc 3 look like this? Well, if you're in this class, I'll assume you probably have some exposure to Calculus 3. In Calculus 3, I do things like this. Let's call Z f of xy. What is my input? My input is an ordered pair. What's my output? A scalar. Oh, my input is the first thing, the domain. My output, this all of Calc 3 actually is this sort of mathematics. I don't input an x, I input x comma y. Then my output is the z. Now you say, well, that will be a point in 3D. Yes, it is, but technically it's input, output. So there's nothing wrong with thinking of it that way in Calc 3. Just throwing it out there. Throwing it out there. Okay, so this sort of notation hopefully is not something we'll struggle over, but it's definitely new. So now we want to talk about something called an element proof. Now, this is the proof we typically will do when we're trying to show 2 sets are equal or one set is contained in another set. And when I say it that way, I mean, we're probably talking about infinite sets. We're not talking about 3 items and 4 items. But so let's go through and make sure we understand the notation. Let's say set A is the numbers 1, 2, and 3, And let's say set B is 1, 2, 3, and 4. Now, the order I write them is not important. All of A lives in B. Would it be correct to say this? Would that be a correct statement? Anybody? Are both of these correct? You say yes or no.
The first
Keep going.
the first one's not, but the second one is.
How come?
Because A is a set, it's not an individual element. And then the second one is
Exactly. Perfect answer. A is a set, it's not an individual element. So A can't be considered an element of B. So the second one, we all agree this is correct. So what do I write here to indicate that A lives inside of B? Do I write 1 as an element of B, 2 as an element of B, and 3 as an element of B? I could do that, but what if A and B were both infinite sets? That might take me all day.
Subsets? You use subsets here?
Yes.
That A is a subset of B?
We use that symbol. I think we've done this before. Now, some textbooks will put the bar in, some textbooks will not. Some will say it's different with the bar, some will say it's not. I could care less. Let's just agree we're going to use that symbol throughout this course, which means we're never actually going to use this symbol. And the funny thing is it depends on the author, depends on your instructor. Some instructors will say, no, I'm going to treat these as different, kind of like less than versus less than or equal. Don't do that. We're not worried about that. It just means all of A lives in B. Could A and B actually be the same sets? Is that possible? Sure. Yeah. In fact, that's a very powerful part of what we're going to do. So that's just from a set containment. So here's the thing in an element proof. There's only 2 types of proofs. You're going to prove one set is contained in another set, or you're going to prove that 2 sets are in fact equal to each other. Those are the only 2 types of ones we're going to look at. So I wanted to do a couple of examples of an element proof, just really, really basic ones. I had one picked out. Give me 1 second. Gotta find which one I was going to do. Oh dear, where did I put it? Hang on 1 second. I had it here somewhere. All right, let's do a really simple one. Let's prove that A intersect B is contained in A. So from a Venn diagram standpoint, I think we all agree with that. Here's A, here's B, here's the intersection. Do you agree that the intersection is in set A? Yeah. I want to prove this, though. I think it's kind of an O-dub, but we want to prove it. So how do you formally prove set containment? Well, there's a strategy, and it's always the same strategy. You start by showing, I'm going to show that if an element lives in this, it is guaranteed to live in this. If I can show that every element in here is in here, then this entire set is in here. I am not saying that everything in here is necessarily in here. In my picture, I have things that are in A that are not in the intersection, but I believe everything in the intersection is in A. So the structure and format of an element proof is pretty much the same. So I'm going to start with something trivial that we all agree. You have to believe it first. So your first thing would be, suppose X is an element of the intersection. You always start that direction. Okay. Now, what does that mean? Now we have to use, what is the definition of an intersection? This is how I started class today. What does this mean? Then X is an element of A or and, which is it? I give myself way too fast. Is it or and? Intersection.
And
X is an element of B. And it's good form to say, by the definition of set intersection. That's my justification. Okay, now what? Well, I'll put I always like thus is part of my conclusion. Thus, X is an element of A because we just said it's A and B. So what's true? We show that X being an element of here, guaranteed X was an element of here. So A intersect B is actually contained in A. Now, this was rather trivial and we already knew it's true. That's not the point. It's how do I start the problem? I start with X being an element of the first set and showing that guarantees it's an element of the second. That's how you get set containment. When there's more going on, that process can be a little bit complicated, okay? It can be. Okay, now that was fairly simple. Now let's do one where we actually do an equals. Okay, how do you prove an equal? So which one did I want to do? Hold on. I want to prove that A union A intersect B is A. So I want to prove this. A union at the intersection being A. Again, it's not even a question of, well, is this an important conclusion? No, it's not the conclusion that we even care about. It's the process of how to prove this. Because of this, we'll be able to prove all of the things like commutativity, distributive property. Heck, this is how we prove De Morgan's laws. This is how De Morgan's laws are proved, by using what's called an element proof. I believe one of the quiz questions I've asked you was to prove one of De Morgan's laws. You know, it's kind of funny. Last semester, one of the questions on the quiz, it's basically prove one of De Morgan's laws, right? That the union of the complements is the complement, of the intersection, that one. And I say, prove this, and the student says, well, by De Morgan's law, it's true. I'm asking you to prove De Morgan's law, and by De Morgan's law is true, is what they actually said. Then they wanted to argue there was nothing wrong with their reasoning, except that you can't assume true what it is you're asked to prove is true. You kind of need a different route. Now, I think we all agree this is true. So what I need to do is I need to show that A union, the intersection, is contained in A, and that A is contained in A union, the intersection. Say, what? Well, if I show containment one way, then basically it means that this set could be smaller than this set. But if I show containment the other way, then it means that A could be smaller. Oh, but if I've shown each set is contained in the other set, one set can't be bigger, one set can't be smaller. That would be kind of similar in baby algebra. If you showed that A was greater than or equal to B, and at the same time that B was greater than or equal to A. If you could show that in algebra, wouldn't this mean that A has to equal B? I think we all agree. Now, you never had to do that in algebra. But if A is at least as big as B, and at the same time B is at least as big as A, then they'd have to be the same numbers. Oh, if all of this set is inside of this set and all of this set is inside of this set, that could only happen if they were exactly the same sets. So that's why you have to show containment both ways. A lot of times I'll only ask you to show it in one direction, but we'll do it in both directions. So we start off by, it doesn't matter which one, let's start off by showing this one. So I have to start with an element being on the left side. So we will suppose, I'll put a little one because we got to do it in pieces. Suppose X is an element of A union A intersect B. Well, if X is an element of a union, that means X has to be in one of those two sets. Okay, then X is an element of A, or X is an element of A intersect B. By the definition of set union. Okay, X is in A or X is in AB. Now that doesn't guarantee that this is an A yet. But now,
Professor, is that supposed to be X in A or A in A?
Oh, thank you. Yeah, that should be standing too close. Thank you. Now, the left side is fine, but I got an or here. So right now I'm not guaranteed that X is in set A yet. It might be in set A. Let's look at this statement then. So now X is an element of A intersect B means X is an element of A and X is an element of V by the definition of set intersection. So what have I got now? I've got X is an element of A or X is an element of A. So X is an element of A, therefore A intersect the, A union the intersection is definitely contained in A. I just showed that X being in the left side guaranteed that X was in the right side. How? Because it was X is in A or X is in A and B. So everywhere I look at it, X is in A. That wasn't complicated. That's not the point. We're done with the first half. Now the second half, I'm going to do the same problem, but now in reverse. Okay. So now we're going to say, suppose X is in A. Now I got to show if X is in A, then what does that mean? If X is in A, then would you say it's true that X is in A? Whoops. Which way am I going to go? Then X is in. If X is in A, oh, sorry, we're doing the union here. Then X is in A or X is in A intersect B. There we go. If X is in A, then definitely X is in, guaranteed to be in at least one of these because it's already in A. Okay. If X is in A intersect B, then X is in A and, I should put, oh, right, and X is in B. So X, oh, I'm sorry, I'm gonna run out of room here. So X is in A union A intersect B, and thus we have done the right side. Therefore, this is getting hard, sorry. Didn't leave myself much room here. A union A intersect B. Now, at this point, you would say, since we have shown containment both ways, this statement is true. More often than not, I'm usually just going to ask you to show containment in one direction. You can show it in one direction, kind of a given. You'll probably show it in the other direction because it's similar reasoning, but things have to be in a different order. Okay, so things like proving De Morgan's laws are true are really kind of fun because you're using some of this interesting information. Let's prove, for example, what we want to prove the set subtraction law. What if I want to prove that A minus B is equal to A intersect B complement? I want to prove this. Well, we believe it's true. This is a really important law, but I said it's a really important law. Can we actually prove it? Well, it turns out all of the set laws can be proved, and all of them can be proved using element proofs. You see, once I have my set laws, I use those set laws, right? Remember, like the negation and the complement law and all those kind of things. We use those to prove bigger statements, but how do you prove the original statements themselves? So this one is fairly simple. That's why I want to do it. There are complicated versions, and I don't need complication. We just want to do the basics. So we'll do the first side. So we always start by suppose X is an element of A minus B. Now, all you're really doing are definitions of things like, what does it mean to be in a set? What does it mean to be in a complement of a set, and so on. So what does this mean? This means what? Suppose X, then X is in an element of A and X is not an element of B. That's what it means. A minus B A minus B means B has been removed. So X cannot be okay. So if X is in the A minus B, Now, what does that mean to you? Well, what does this mean? Then X is in A and X is in B complement. And why? That's the definition of, by the definition of complement. So X is an element of A intersect B complement, because I'm in this set and simultaneously in this set by the definition set intersection. Thus, okay, I'm just going to go the one direction. The other direction is actually easier in this case. The idea being, if I can show being in one guarantees you're in the other, then you have shown containment in one direction. If I put a statement that was not true, you can't get containment. It's not possible. A lot of times it feels like, well, we can make anything work in this case. No, you can't. And you're going to be using mostly unions and intersections and complements. You're going to be using these concepts over and over and over again. So the concept of an element proof is I can prove big properties by using an element proof. Okay, I want to do another one. I'll find it now. Hold on. I made myself a little chart of things I wanted to prove. De Morgan's law is quite cool, by the way. Oh, I wanted to do one of the absorption laws. Again, these are fairly simple things. We would like to prove, let's see, which one did I write down here? Oh, actually, oh, you know what? Never mind, I already did that one. I was going to do one of the absorption laws and I just realized I already did it. All right, let's see, then let's do instead. Oh, let's do the one of the distributive laws, A union B intersect C. Make sure I wrote that down correctly. Yes, I want to prove this one. So we'll do just the containment in one direction. Again, just to save time, and plus my board is not that big. If I want to prove this, then I either start with the left side and show it's contained in the right side, or I start with the right side, show it's contained in the left side. It really doesn't matter which way you go. So let's do, and usually we start with something like this. Let A, B, and C be sets. Now, the thing is, it doesn't matter if a set is empty. If this is true, it's always true. There's no exceptions to this. Now, I could try to do this. I could try to demonstrate what this looks like using a Venn diagram. There's nothing wrong with that. But it starts getting a little bit dicey if you're using Venn diagrams with more than two sets, sometimes just to get the interpretation. So let A, B, and C be sets. And suppose that X is in A union B intersect C. Okay. Now, just that's it. I haven't done anything yet, but this is my supposition. So now, if X is in the union, that means X has got to be in one of them. So that, therefore, we can say that X is an element of A, or not and, X is an element of B intersect C. By the definition of set union. Okay, this statement is unquestionable because that's what it means to be in a union. Now, if X is in A, that makes the rest of this fairly simple. So hold off on that for a moment. Let's look at the other side. If X is in B, intersect C, okay? So if X is in A, if we just stopped here, if X is in A, then X is definitely in the union. If X is in A, then X is definitely in the union, and therefore, and that's not all that exciting. So let's continue on this part. If X is in B intersect C, then X is in B and X is in C. By the definition of set intersection. Now we have something. Okay. So let's start with this. If X is in A, then X is in A union B and X is in A union C. By the definition of set union. Now, again, if X is in A, then X is definitely in A or B. I probably should have wrote that down. And if X is in A, then X is definitely in A or C. Okay, so X is in this union and X is in this union. So X is an element of A union B intersect A union C because it's in both of these simultaneously. By the definition of set intersection. And we're not done. That was, I said, if X was in A. I have an or here. Okay. I have an or. So the second part of this, now I'll say if X is in here, if X is in B intersects C, we already said if X is in, then X is in B and X is in C. I guess I could have waited to put the, then X is in B and X is in C. And we already said by definition of set intersection. So X is in a union B and X is in a union C by the definition of set union. I'm gonna have to come back to the top. So going back to the beginning, I'm taking two routes. I said, okay, the first statement says this is true or this is true, this is not an and. If this part was true, that led us to X is in this. Okay, second half. Forget that. Let's assume this part is true. In fact, it's safer to say it this way. Assume this is true and this isn't. Then X is definitely in here. Assume this is true and really, in a sense, assume this isn't. So if X is in the intersection of B and C, then X is in both B and C. Therefore, X is in A union B because X is in B. X is in A union C because X is in C. So therefore, X is also in the intersection. Okay. I guess, okay, so X is in, boom. I'm gonna go back to the top, sorry. I have to do this. I hate erasing. So after that last line, we've got X is in A union B and X is in A union C. So X is in A union B intersect A union C by definition of set intersection. So if we stop right now, what we showed was that if X is in A, X is in this. If X is in the intersection, X is in this. So if X is in either one of these, then X is in this. That's what we needed to show. We showed if X was in either one, that conclusion is guaranteed. Thus, A union this is contained in A union B intersect A union C. It's a bit of a game. It's a bit of a game. Now, what's going to happen next day is today we're basically proving all the laws in a sense. That's kind of your goal is, can you prove all of the laws? Commutativity, identity, item potent, absorption, set difference, distributive. We're looking at a lot of them. De Morgan's are the funnest ones to prove. They're probably the easiest ones to prove. So assuming we can prove all the laws, I don't need you to prove them all, but you have to understand how to prove them all. Then next day, what we're going to do is take complicated statements, and I'm going to say, justify this. And you're going to say, oh, it's true by the commutative property, by the distributive property, by De Morgan's law, because now we believe all those laws are true. I know you already believed them anyway, but now we're able to actually prove that they're true. And all of the proofs involve what's called an element proof. Now, I put a couple of examples online if you've had a chance to look at some of the posted notes. This is not complicated. Now, this problem here is fairly complicated because it's really, really big. I don't really want you to concentrate on the really big ones. So as you're going through the text, I would suggest do smaller problems. And again, if you're showing equality, all you have to do is show containment both ways. If you're only asked to show containment, then you're done with one direction. So it's really not that complicated. Showing containment in both ways often involves a lot of the exact same steps, but kind of in a reverse order in a sense. Okay, well, that's where I wanted to get to today. So let me go and stop.